We're now recording.
Mhm.
Uh, right. In a few minutes, we'll have Adam Hibberd and Marshall Eubanks, which is our feature talk today. But before that, I'm going to hand over to my colleague Mark.
Good afternoon, everybody. Well, normal format, a brief introduction from myself today, and then we'll be straight into Adam and Marshall for their talk, and then, as usual, be over to questions. So, if you could move on, Bob. So, normal announcement. If you're not already on our contact list and you'd like to be kept informed of what we're getting up to and the events, do send an email in. And if you're interested in helping running the branch, again, send an email to the West Mid Sec because we would love to have some help. Okay, Bob. I'm afraid I've got some sad announcements now. Some two friends and colleagues have passed away. First off, Dr. Peter Penny passed away on the 3rd of September. The Pete's the obviously the gentleman in the middle there. That's a picture from the when I first met him in the late 70s, maybe very early 80s. Um, Pete joined the rocket propulsion establishment at Westcott back in '64. He was a Sandwich student and he was doing physics. He got his degree in '69 and went on to do a PhD, which he got for, as you can see there, research into solid propellant burning rates. And one of the topics he was particularly interested in was erosive burning in solid propellants. Um, he worked for another uh, BIS luminary, Bob Parkinson, who many of you will be familiar with, as a ballistician at Westcott. So a ballistician, for those of you that don't know, is what those of us in the rocket industry call a rocket scientist. I'm not a rocket scientist, I'm an engineer, but Pete was one of the top rocket scientists in the country. Um, Working for Bob, he also did various bits in support of Project Daedalus, which I'm sure many of you are familiar with. He went on to become technical director at Royal Ordnance Rocket Motors Summerfield, which is up here in Kidderminster. As you can see, he was the author of a book on internal ballistics of solid propellant rocket motors. Um, Fascinating item, well worth a look if you're mathematically minded. Um, and Pete was also one of the founding members back in 2011 of this branch. Pete, John Harlow, and myself formed were the original members of the branch. Pete will be much missed by all of those that knew him. So thank you, Bob. And then another sad announcement, unfortunately, Hugh Nicholson. Um, Hugh was originally he passed away on the 7th of September. He was originally from Newcastle and saw a job advertised. He was a draftsman and he saw a job advertised in the Midlands on rocket motors. And he thought, oh, I'm interested in space flight and rockets of the time. And hello, we've lost the. Thank you, Bob. So he applied for the job and got the job as a draftsman at the newly formed Summerfield Rocket Research Station, which was which was part of ICI. Um, he very quickly moved into project management and project engineering, and he was a project engineer from the 1950s to the 1990s. And for a lot of that time, he was a member of the British Interplanetary Society. He was always very interested in space flight. He's an author of two books on the history of Summerfield and its technologies. Again, Summerfield as I mentioned, is a rocket research establishment primarily concerned with a particular propellant called cast double base, which has lots of use for military rocket motors. Um, he attended many and supported many of our early events here in Droitwich, both at the library our talks at the library and the space days. And then as he got older and he was unable to travel, he dialed in and supported from afar. So he was ever such a nice chap, and he'll be much missed by everybody that knew him. And normal thing, if you're not a member, please do consider joining the BIS. There's lots of good reasons to join, as you can see there. Move on, please, Bob. And again, please join the BIS. Thank you, Bob. If anybody is a budding author and wants papers or material published on spaceflight, we have a number of excellent magazines. There's JBIS, the long hair magazine, if you like, Space Chronicle, the History magazine, Space Flight for the Populist magazine, and Odyssey, which is has more of a science fiction focus and is excellent, an excellent read. So if you're interested in contributing to those, please do contact the editors. And of course, if you want to get copies, please join. Thank you, Bob. Finally, you'll be relieved to get rid of me. Today's speakers, over to Adam and Marshall. Looking forward to this talk. I hope you enjoy it.
So Marshall and I today are going to be talking to you about missions to a asteroid that was discovered December 2024. And we're talking about the research that we conducted and wrote up in a paper, which is still being processed by the journal that we've applied to. And I'm just going to discuss to you, first of all, the method we used to solve the issue of sending a spacecraft to this particular object. And what we used was this software tool, which is called Optimum Interplanetary Trajectory Software, which was entirely developed by myself in Coventry. That was in April 2017. I constructed the software in 2017. Development took 4 to 5 months. It uses a nonlinear problem solver known as Nomad, and I'm not going to go into detail there. But the most important thing is it uses a software library called SPICE. And SPICE allows you to determine very accurately the position and velocities of objects within our solar system. So that's very important if you're going to plot a mission to an asteroid, for example. And it's on GitHub, which is an open source repository. Okay, so I'm going to explain to you, I'm going to endeavor to explain to you exactly how OITS works, as I put it, OITS. This is the software that I developed. And we're going to assume, first of all, there's no gravitational field, okay? And we have 2 points, A and B, and we want to get from A to B. And there's a displacement between them. They're separated by a distance delta r. But also, we want to be at A at time TA and B at time TB. And that means the time elapsed is naturally TB minus TA. And what we do is travel on a straight line because there's no gravitational influence on that spacecraft. And the velocity needed is delta r over TB minus TA, simply position over time. So that's what we do. But of course, reality is more complicated than this. So we have to introduce the sun, and we're going to do that now. And if we attempt to go straight to B, then the sun's gravitational pull will perturb the spacecraft. So what we have to do is counteract that pull by firing slightly outwards. Okay, and this velocity here is the velocity required to get from A to B in that elapsed time. Now, just bear that in mind, this is the velocity needed. But as we've introduced a gravitational influence, that means there are in fact 2 possible routes that we can take. Unlike the case where there was no gravitational influence, it's just a straight line. Here there are 2 routes, and this is the short way that I'm showing you here, which is prograde, I guess. And there's also the other route, which is retrograde, I suppose, and this is the velocity needed to travel on this route. It goes out of the screen and comes back on again, and then arrives at B at time TB as required. So there are 2 possible ways to get to this object. Now, what do? We decide which way we want to choose, which way we want to go. Okay, so what way do we go, short way or long way? Well, that all depends upon the velocity that you're traveling with already. Okay, so let's say we have A as a planet traveling with a velocity VA, and that's the arrow there, and B is another planet also has a velocity VB. Now, how do we get from A to B? Well, what we need is for a flyby mission. That's where you arrive at the target, that's point B, and fly by it without applying any thrust to slow down or match velocities with it. What one does is, if this is the velocity that the planet is traveling with, and this is the shortwave velocity that we need, we apply this delta V, a velocity increment to our VA, and we get to the required velocity, which enables us to get to B. But there's also the long way as well, of course. So that's the long way. This is the green dashed line here. This is the delta V needed to take us the long route. Now, which one of those do we choose? Delta V SW or delta V LW? Well, we choose the one with minimum length. So the arrow is minimum length, and that makes the most easy solution to arrive at the target within those specified constraints. With a rendezvous, it's slightly more complicated because we want to match velocity with the target when we arrive. So there's another delta V that we need to introduce. And there it is. We've got two delta Vs, short way there and long way there. And the way we choose is simply the sum, the minimum sum of the two, which in this case is short way is again, okay? So we go the short way for the rendezvous mission as well as short way for the flyby mission. So there we are, a simple description of how it works. But our objective is this asteroid called 2024 YR4. And Marshall is going to later explain exactly what all this is about. For the moment, we're just going to treat it as a target for astrodynamic research. This is the paper that Marshall and I wrote. And we're going to introduce a few definitions. These are important parameters that we must be conscious of when we plan mission to this object. So that, as I've explained, there are various different mission scenarios. So we could fly by it where we arrive at the target and we stay traveling in the direction we left. We arrived at it with. Rendezvous is actually where we apply a delta V to match velocities with the target once we've arrived. So that needs onboard propulsion in order to attain that velocity. And then the sample return is where we go to the target and we collect a sample of material from that target, and we return to Earth, and Earth is there, and we just capture the capsule which has the material that we need to study. So that's the sample return option. So first of all, I'm going to talk about flyby mission, but first of all, I'm going to explain some other parameters. So first of all, we have hyperbolic success speed. This is the speed with which the spacecraft will exit Earth's sphere of influence. So if you imagine there's a theoretical radius whereby if a spacecraft is outside of that radius, then it's only influenced by sun. But if it's inside that radius, it's only influenced by the Earth. And so the hyperbolic success speed is with the speed with which the spacecraft will exit that sphere of influence. And the characteristic energy is simply the square of that. And the reason why we need this is because when you have launchers, their performance with respect to escape missions, which is what we're dealing with here, depends upon C3. So the higher the C3 value, then the lower the payload mass, the more energetic the orbit that we need. And the lower the C3 value, the higher the possible payload mass. Okay. The arrival velocity is what it obviously is. It's the velocity with which the spacecraft arrives at the target with respect to that target velocity. And the delta V, if you have a rendezvous mission, then this is the arrival delta V, the velocity you need to apply in order to stay with the target. Okay, so that's flight duration is the duration that the trajectory takes. Okay, so the results, let's go into this. For a flyby mission, what we can do is produce a pork chop plot. I'm going to show to you now a pork chop plot, and we'll try and explain it to you. So what we have here is on the horizontal axis, we have the earliest launch date, 2025, to the latest launch date, 2033. And the flight duration here is on the vertical axis. Now, it so happens that if you have a mission to an object, a direct mission, that trajectory only depends upon the launch date and the flight duration. So if we know both of those things, we can work out the hyperbolic excess speed. And the lower that hyperbolic excess speed, as I've explained, the more viable the mission. So in other words, the darker these bands, the more viable the mission. So we have two dark blue bands here in 2028, and 2 dark blue bands. You see the diagonal bands in 2032. So that means, in fact, there are 2 opportunities up to 2033 whereby we could send a spacecraft to fly by this object. Now, we can go into more detail here, which I shall do now. We're going to zoom in on 2027 to 2029 there. That's the horizontal axis. And what we have here is the red dashed line is the characteristic energy, which I defined to you earlier. And the lower the characteristic energy, the higher the payload mass. And we find for April 2028 launch, this red dashed line hits the 0. So in other words, the characteristic energy is 0. So that makes it a very easy mission as well. To conduct this flyby mission would be very straightforward. And in fact, you could actually launch, if you look at the plot, this is a logarithmic scale on the right-hand side for C3. You could launch throughout 2028 without any problem at all and realize a mission to this object with no trouble. And we have the blue solid line here, which is the arrival date, and we see that before January 2028, the arrival date is around about October, and after that, it's about December. Now, why do we have these 2 arrival dates? It's simply because, and I'm going to show this to you now, this green ellipse is the object that we're trying to intercept, and the blue circle there is Earth's orbit, and you can see that this 2024 YR4 intersects the orbit of Earth at 2 points, essentially, looking down from above. And the first point is in October, and the second point is December. So that's why we have 2 possible solutions. One arrives at October 8th, the other arrives to December 20th. Okay, just moving on. Let's look at the second detail, which was from 2031 to 2032. And we see in a similar situation where the characteristic energy is very small indeed. So we could indeed do a flyby mission to this object without any difficulty in 2032. So we'll now go on. Those are the conclusions, which I shan't stay with that too much. I'll go to rendezvous. So a rendezvous mission is where, just to remind you, that we apply a delta V to stay with the object once we've arrived at the object.